Alright students, today we will start a new topic which is relations, and this is somewhere you can say very important as per se your JEE mains. Why I am saying this is important? Because generally a question is being asked of this particular chapter, and the chapter is a easy one. Why we call this as a tough topic, I don't know, but yes, it's tough because we do not do it in a proper way. So today in this particular lecture, we will try and cover all the things related to the relation topic and see that we fetch those 4 marks which are very crucial for your JEE mains. Alright, so let's start with this particular topic. So let us start with the basic definitions first of all. So the first definition that you people have to understand is the cardinality or the cardinal number of a set. We all know that a set can be represented as a capital element A, and its elements are written in curly brackets. So let's say if I want to write a set which has 1, 2, 3, 4 in it, so I can say A is a set comprising of elements 1, 2, 3, 4. Okay, so what is cardinality? The number of elements in the set, and it is written by n A. So n represents the number in the set A, and we can easily see that it is here 4, right? Got it? In fact, the set A could also have been a alphabet. That is not a problem. So A, B, C, and D. Then also the cardinality would have been 4 because the number of elements in the set A is nothing but equal to 4. What do you mean by the other definition? That is singleton set, as the name suggests, single. So if there is a single element in the set, then the element is known as, or the set is known as singleton set. Okay. So for a singleton set, NA would be nothing but equal to 1. There will be only one element in the set. For example, I have taken here that X is a relation where X is belonging to natural number, and X ranges from 1 to 3, where 1 and 3 are not included. So there is only one natural number which satisfies this. You can say 2. So there is only one element in this particular set, right? That is X equal to 2. That is why I will call this as a singleton set, because only one is there. Okay, let me just talk about the null set. So null set is when the set is empty, right? When the set is empty, void or null, all are the same meanings, and it has no element, right? And we generally represent this by null. Null means generally represented by a phi sign. So for example, I have written over here, let's say you are trying to solve x square less than 0 for x belonging to real numbers, right? So if I say this, it has no solution. In terms of way, you will say me that the answer is no solution, or in terms of or in terms of set, you will say x does not take any real value, or x belongs to phi. The solution to this set is phi set. Okay. Though there is a difference between what I have written over here in a singleton definition, let's go just through quickly over it. If I write phi in this particular fashion, if phi is a subset, right? So when you say that I have written like this, so this becomes a subset. So for example, you have defined a set A, something like this. So now this will not be counted as an empty set because it contains a element this. So if I ask the cardinality of this particular set, then the cardinality would be 1. Cardinality will not be 0. Okay. So whereas if I say that it is empty, right? It is empty, then it is here cardinality will be of an empty set, let's say, will be equal to 0 for null set. Okay. Please understand that difference. Next definition that we have to do is the equivalent set. So for equivalent set, let me take an example. So A is a element which has, let's say, 1, 2 and 3, and B is a set which contains A, B and C. So here these two are equivalent. So for equivalence, what we check, that number of elements in set A should be equal to number of elements in set B. Very basic stuff. And when will be the two equal? So minded, the word is equivalent and equal, completely different. So the sets will be equal when every member in A is a member of B and every element in a B is a member of A. So that means they are actually equal. So if you want them to be equal, then B should also be 1, 2 and 3, obviously. Okay, I hope these basics are clear. Now let's talk about the subsets. So you people are always familiar of these subsets because you have been doing it for a long time now. So let me just quickly take an example to brief you what is subset. So if A is the set like this, right? And you call that B is a set consisting of first 10 natural numbers, right? Let me take it this way. Okay, so A will be known as the subset of B because it could be derived from B, right? All the elements of A are actually existing in the set B. So how do we write that A is a subset of B, or you can say it is derived, and this is the mark or the syntax of subset, right? How do you find the number of subsets that could be formed? So let's say if B here is, let's say 1, 2, 3. I'll just now take another example, right? 1, 2, 3. So if you use the elements of set B, if I am using elements of set B, how many subsets are there? Elements of set B to form subsets. So how many subsets could be there? Let's take an example now. So if I talk about the subsets of B, let's say subsets of B, let me tell you how it could be. So one could be the null set, right? Nothing has been selected. One could be that you select only one element. So you select only one element. So 1, 2 and 3. Then you can select two at a time, right? 1, 2, you can say 1, 3, and then you can say 2, 3. Okay. And the last option could be that you say all of the three are selected in the set. So these are the total number of subsets that are available, and if you count them, they come out to be equal to 8, right? This is how we do it. Now, if we want to convert this into a formula, let's see how we'll do it. And before going further, also understand that when I say here 1, 2, right? 1, 2, it is equivalent to saying 2, 1. So we will not count 2, 1 as a different entity or a different order or a different set. It is the same subset because it consists of same numbers. It is just that you have written 1 over here and 2 over here. So in a way, when I say set, they are not the ordered sets that we remember. So 1, 2 in a Cartesian system or a Cartesian coordinate system, these two are different points. But in terms of sets, they are same because set consists of numbers. So the numbers in these two are actually equal. So they are both same. They are equal. Okay. So if we were to say, how do you find number of elements in the or number of total subsets formed using the elements of B? See here. Here is now if I take about PNC topic here, so you can understand with the help of PNC. Selection. So you select 0 element here. In these three cases, you select one element at a time. In these three elements, you select two elements at a time. And in these, you select all the three at a time. How many total elements were there with you? There were total elements were 3, right? So now you have an option to choose 0 element. You didn't select anything, that is 3C0. In how many ways you can select 0 out of 3 is 3C0. Then you could select one at a time, that is 3C1. That is why you are getting 3 answers. Then you could select 2 at a time, that could be done at 3C2. And then you can select all the 3, that is 3C3. If you calculate, this comes out to be 8, or in fact, better way of saying it is 2 raised to power 3. Why 2 raised to power 3? Now you have to just remember the formula from the binomial that we just did earlier, that NC1 plus NC2 plus NCN is nothing but, yes, 2 raised to power n. So this was the formula from binomial, right? Binomial expansion. So you just need to remember that the number of total subsets that could be formed from n particular elements is 2 raised to power n. In fact, I would like to highlight other way which you people can also remember this. So what that process could be, let's say, so there are n elements with you, right? There are n elements. So let's say there is 1, 2, 3, 4 and so on. So one has two options. Either it could be selected or it could not be selected. Same is the case with 2, that it could be selected, not selected in any of these subset. 3 also has two options, selected, not selected. 4 also has two options. So there are n elements. Now we draw the dash diagram, right? All of them have how many options? They can be selected, not selected, selected, not selected. And if you see, they are all 2 and they will be multiplied. So it will be 2 multiplied n times. And what this answer comes out to be? 2 raised to power n. So this is also the other way of calculating number of subsets that you can form out of n particular elements. So both of the logics are different, but conceptually they will give you the same answer. Alright, so I hope the fundamental is clear. Now let us study different types of sets that you can understand. So there are two types of sets, that is proper set, right, and improper set. And improper set that you can form actually from set of items given to you, right? So proper set, if you ask somebody what is the proper set, so for proper set, A should be a subset of B, right? An improper set would look something like it could be equal to B also. Okay, So it could be equal to B, subset of B, or equal to B. So what do I mean by this? Let me just go in depth of this. So improper subsets actually are actually of two kinds. Okay. So improper is, so let's say if there is a set A will always be the subset of A, always be subset of A itself, right? And we know that phi will always be subset of A. So these two elements, that the set itself and the phi set, are every time the element, every time the subsets of any set that you take. So that is why we do not call this as proper sets. In fact, we call them as improper sets. So if I take that there are A which has here n elements, right? It has n elements. So the proper sets of this particular set, proper sets out of this A would be what? Their total were 2 raised to power n minus these two, because they are anyway always the answer, right? So this is called number of proper sets. So you will have to exclude the set itself and the null set to find number of proper sets. Okay. The other term that you people also will hear is that superset, right? So it is nothing but it's the opposite of subset. So when I say that A is subset of B, so you here read it as A is subset of B, right? So other way of saying is that B is superset of A. The other way of saying it. So B is superset of A, but the internally they both work the same way. A is the subset of B or B is the superset of A. They are actually the same terms. Got it? So next is something very interesting. It is power set. So what do you mean by power set? It is the collection of all subsets of A. So let me take an example to make you people comfortable with this particular property. So A is a set which contains three elements, 1, 2, 3. How many different subsets could be found? So let's try and start with the subsets. So subsets could be, one could be yes, phi, the other could be 1, right? The other could be 2. We just did it earlier, right? Remember? So these 8 will be the number of subset. 8 subsets can be formed. So the value, if we asked, so how will you say that how many number of subset can be formed is basically power set. The total number of subsets that you can form out of a particular elements of a set is actually power set. So how do you write that? Number of elements or the cardinality of the power set of A is nothing but 8. And we have already did the formula for this. So if you need to find the cardinality of the power set, it is nothing but 2 raised to power n. An interesting concept here is, let's say if somebody asks you n power set of A. Now you can say that it is something working as a composite machine, right? Okay. So the answer would be what? 2 raised to power n. So the chain would also expand in the exponential series. This is how you can actually remember this. So if I ask the cardinality of power set, then what you will say in this particular answer? Yes, it will be nothing but 2 raised to power 2 raised to power 3, right? This is the answer. So it will be nothing but 2 raised to power 8. This is what we were actually looking for in this particular answer. Why this is happening, let me explain it to you. So now this is your power set of A, right? Now you want the subsets to be formed out of this. Now you want subsets to be formed out of PA, right? Not A. So consider this, it's a 2-chain process. So actually this is, now you are going to do level 2. So when you made subsets from this to this was level 1. Understand it this way. Okay, so from A to PA. Now you from PA, you want to go to P of PA. That is the second level. So now what you will do, how you did this calculation, just revise it. So how do you find number of subsets in PA? That what you did in A, there were, you said, sir, there were 3 options, right? I told you just in the previous slide how to calculate this, that one could have been selected, one could not have been selected. Similar 2 options would have been for 2, and similarly 2 options would have been for 3. That is why 2 into 2 into 2, that is why you get 2 cube, right? So that is why you answered me 8. Now what is happening with the level 2? So now level 2 does not have 3 elements. Now you want to form subsets using this particular set. So this is the new set that you people have. So, or in fact, this is the set. This is the set for P of PA, from where you will start building the subsets, right? So how many elements does this set has? 8, right? So you will draw 8 dashes, right? And each element now again will have how many? Yes, each element will have two options again, whether again selected, not selected, selected, not selected, selected, not selected. And if you multiply, this comes out to be 2 raised to power 8. Can you see that the answer is same? So we did nothing, but we just hypothesized this formula into a proper notation. That's it. You just need to remember. So if somebody asks you the triple layer, right, that N, P, 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 A. Can you tell me the answer now? Yes, do not get afraid. So you just raise the level again. That is the answer. I hope this concept is now clear to you. So let's talk about the Cartesian product. So what do you mean by Cartesian product? So there are two sets. Let's say A. So A has, let's say here M elements, right? I am talking about A, M. It has M elements, right? Written over here. And B has some N elements here in that set, right? And you need to find something called product, right? Cartesian product, and it is written as A cross B. So now what do you mean that you are trying to form ordered pairs? You are trying to form ordered pairs using set A and B. So what you will say, ordered pair A comma B. Here A will be an element from A and B will be an element from set B. So this ordered pair is nothing but the Cartesian product. That is what we say. So in fact, all your Cartesian coordinates are, yes, Cartesian product. Can you now figure out the same terminologies? Okay. So if somebody asks you that it has n m elements and it has n elements, right? So NA is this and NB is, so how many elements would be there in their Cartesian product? Very simple. Answer is M cross N. Right, so the number of elements in their product will be M cross N. Answer is again very simply said that let's say this is A and this is B. So 1, 2, 3, it is something written like this, and this is A, B, and C, and there are, let's say, so many options. So you can order A with all these options. So A will have how many options? Let's say. So for 1 you will have N options because there are N elements in this set. Then for 2 you will also have N option. Then for 3 you will also have an option. So up till this N into N, oh sorry, N plus N plus N would be done how many times? N plus N plus N. Yes, it will be done N times. So the answer to this problem is nothing but M cross N, right? This is how we find this. Okay, and if we want to talk about the universal relation from A to B, another important definition, universal relation from A to B. Okay, so the total number of elements that we can, or total number of ordered pairs that we can form from A to B is called the universal relation. So universal relation here will have M cross N pairs or M cross N elements, right? So all the possible elements that you can form using this cross product will be fall under universal relation. Got it? Okay, now let us start with the basic definition of relation. So first of all, let us understand what do you mean by relation. So firstly, it is written something of X goes to Y, something like this. So you can understand in this way that there is something relation, some logic R from which the elements in X are related to elements in X or in elements in Y. So for example, I have taken a beautiful problem from Ramayana to understand what is a relation. This is what a diagram which I found over the web, and I found it to be really interesting for you people. So the relation going from X to Y, you can see the arrow. So relation is from X to Y, is the relation between, yes, the relation is wife. So Dashrath has 3 wives which are written here: Ram, wife Sita, Bharat, Mandar, and so on, right? Shatrughan, Shruti, and all this stuff. So the relation given over here is of wives. So I can say X, the elements in this have wives, elements in this related to these and those, so on. So how do you define a relation? That number of elements in X. So just let me highlight it for you. So correspondence. So correspondence is a correspondence between, correspondence you can understand a relation or a mapping between set X to set Y, where some or more elements of X, some or more, right? It could be all, it could be some, are associated with some or more elements of Y. There has to be some logic by which the elements in X are related to some elements in Y, right? Okay. Remember that, yes, X has to be non-empty and Y also has to be non-empty. You cannot relate an empty set to an empty set. That's absurd. Alright, so this is the basic definition of, or how we talk about relations. Let's see what different kind of relations do we have. The first type of relation that we have to study is reflexive relation. So for reflexive relation, let's understand first of all, what do you mean? So if there is a relation from X to Y, it is said to be reflexive if X or X belongs to X. So if there is a relation where the element in set A is related to itself, right? So it must be related to itself, then it is called a reflexive relation or a reflexive mapping. Let me take an example for you people to highlight that how this actually works. Right, so I have taken A to be set consisting of 1, 2 and 3, right? And if I want to draw, let's say, relations which are reflexive out of using these elements of this set, so they would be 1 is mapped to 1 itself, 2 is mapped to 2 itself, 3 is mapped to 3 itself. So this is an example of reflexive mapping. You can say this is an example of reflexive mapping where the element is again, yes, mapped with its own self. 2 with 2, 3 with 3, 1 with 1. Now let me talk about a relation again where 1 is again mapped with 1, 2 is mapped with 2, 3 is mapped with 3. Then there is 1 comma 2 as well. So now can you tell me whether this would be reflexive or not? This would still be reflexive. No problems at all. Why? Because reflexive means that this definition should be satisfied, that they should have images of the number that is already there, right? If this is satisfied, the other images are also there. That's not a problem for me, right? So if 1 comma 1 is there, 2 comma 2 and 3 comma 3 is there, then 1 comma 2, 1 comma 3, 2 comma 3 are there. It doesn't matter. Still the element or this relation, particular R2 relation, will be known as a reflexive mapping. Let me take another example of a mapping from this particular set. So it says 1 comma 1, 1 comma 2, 2 comma 1 and 3 comma 3. Now what about this element? So this is now not reflexive. I would say this is not reflexive. Why? Because it is missing which element? It is missing your 2 cross 2. So this is not reflexive. So it does not mean, people generally make the error that they understand reflexive only as this particular example. This is not the example of a this is not the only example of a reflexive mapping. This is also the example. So you could have more elements apart from A comma A, right? So if A is a mapping, or let's say elements are A comma A must be there. This is the definition, must be there, but it has not said that this must only be there. It is not saying must only be there, right? So understand this difference. It must be there, this is required, but it is not necessary that they will only be there, no other relation could be there. Got it? So this is what you mean by reflexive. So A comma A, if is there in the set X or relation, that means it's a reflexive relation. Next is the identity relation. So it is actually a part of your reflexive relation only. So I can say that identity relation, okay, here is nothing but it's a subset of reflexive relation. It is deriving its property from there only, but with some constraints that you will be able to understand very well. So if I say A comma A, you understand this is symmetric. The condition for identity also remains the same, but with a highlighter that only. So if every element of X is related to itself only, then we call this as an identity relation. So let me just take an example to make sure that you get hold of what I'm talking about. So here it is 1, 2, 3. Let's say write the first relation, that is 1 comma 1, right? Then we can say there is a point 2 comma 2, and then there is a point 3 comma 3. This is a relation that I have written. So can you see that every element here is again mapped to itself? So this is not a problem. This is identity element, or you can say this is your identity, or as well as reflexive, not a problem, whatever you want to say. Both relation, reflexive or identity. Let me take R2 element now. R2 relation is 1 comma 1, 2 comma 2, 3 comma 3, and now it has 3 comma 1 also, right? So right now we just did earlier that this is reflexive. That's not a problem. So it is satisfying the conditions of reflexive, but it is not identity relation. So for identity relation, the word is that you people have to understand is only. So it should contain only those elements which have mappings to it own self. So here 3 comma 1 is the odd man out. If I talk about the identity, so this should not be there, right? Otherwise this is reflexive. That's not a problem. Okay, so every identity relation is a reflexive relation and not vice versa. So you can understand and remember that every identity relation, right, is a reflexive relation because it's a subset of this. It's a particular case of reflexive relation. Let's take a very interesting topic that you need to find number of reflexive relations. So though this should not be asked at the JEE Mains level, but still we will do it because if you were to ask a tough question from this particular topic, I would ask you people this. So let's say you are given that A has n elements, right? So this is a set which is given to you and it contains n elements, right? The cardinality of this is n. You need to find number of reflexive relations that can be formed using this particular set, right? Reflexive relations of this particular set. So let's see how do you want to form a reflexive relation. Okay, so how do you find number of reflexive relations out of this? So we know that reflexive relations are of the sort 1 comma 1, 2 comma 2, 3 comma 3, and this will be n comma n, right? So these elements should be there for to make this set or relation. So for let's say this relation is completely what? So this relation is completely reflexive. Can you say that this is reflexive? Now we just did that it is not necessary that for reflexive you should have this. So for let's say another relation R1 can have all these elements, plus it could also have something like 1 comma 2, right? It could also have this. This will also be reflexive. We just studied, right? If you're not clear, just go back and watch the video again. Though this is for sure is identity, right? This is identity. And in fact, if somebody asks you to define how many identity functions are there or identity relations are there, then identity relations are unique. It is always one. You cannot have more than one identity relation of a particular set. Okay. So now let's come back. You want to find reflexive elements. So I'll show you a method called the matrix method, right? Matrix method to understand how you actually need to solve these kind of questions. So matrix method has, let's say 1 comma 1 mapping, 1 comma 2, 1 comma 3, and then it will go on till, yes, it will go on till 1 comma n. Then it could have 2 comma 1, 2 comma 2. Now getting how I'm drawing the matrix, you must have done this in probability, right? Dice problems, just remember 2 comma n, and this will go on till where? Yes, it will go till n comma 1, n comma 2, right, and n comma 3 to form the matrix. So this is the matrix that I have drawn. Now these are all the possible Cartesian products that you can form from A cross A. So now you actually what you are trying to find reflexive relation in A cross A itself. This is your target. Okay, so A cross A has n elements, so yes, it will have n square elements, and it is very evident that you have n rows, right? You have n rows and you have here n columns, so it has actually your n square elements. Now if you just think of you want to have reflexive
relations. So for reflexive relation, let me just again reiterate what you people require. You want these relations to be there for sure. So can you select them? Now just start thinking about the permutation combination logic. So n comma n, you need them very badly. So there is no options, right? You have to select them. You have to select. They are already, in fact, you can say they are already selected. There is no option. Plus, whatever you can pull here is additional. This is additional, right? So you want how many options I can pull in this particular space here. How many sets can, or how many ordered pairs or pairs I can put over here. Then also this will be a reflexive element. So if you just see how many different relations are available for you people. So so there are total, n square elements, right? And if we talk about the diagonal elements, can you tell me what are the diagonal elements here? So these will be the diagonal elements. Yes, and all the diagonal elements will be 1 1, 2 2, then you will have 3 3, then you have 4 4, 5 5, 6 6, and then this will be n. So diagonal elements will form what? They will form the components of your identity relation, right? They will form identity relation. That is why I was saying there is only one identity relation, that is the diagonal itself. How many remaining elements are there? What are the remaining? Yes, that's the answer. You have got it. So the remaining options, so remaining ordered pairs, remaining pairs, how many remaining pairs are there? Total were n, right? Square, and you have selected already n. So this is the total number that you have remaining pairs. Now this is not the answer, believe me. So if somebody answers that n square minus n, this is wrong. Now let's talk about this particular element 1 comma 2. It is one of the n square minus n elements. It could be selected or not selected, again according to permutation. It could be selected, S for selection, and it could be not selected. To put here in this particular range, let me again shade it, right? Same could happen for 1 comma 3. It could be selected, it could not be selected. It could be selected, it could not be selected. So again, every element has how many options? 2 options. And how many numbers are there? So yes, what will be the answer? Yes, so the answer will be 2 raised to power n square minus n. This is the answer. So these are the total number of reflexive functions that can be drawn on a particular element A with having number of elements as n. I hope this is clear. The other type of relation is the symmetric relation. So what does the symmetric relation say? So there is a relation R, right, from x to y. So how it is defined now. So if there is a relation 1 which has, let's say, element a comma b, right, then if the ordered pair b comma a is also there, right, if a comma b is there, then b comma a is also there, then this type of thing is called symmetric relation. This is what is meant by symmetric relation. So if I just repeat what is there in your books, so is said to be symmetric if, so this is if and only if x comma y belongs to the set, then y comma x belongs to R for all x and y belonging to the element R, right? So this is something is what is to be said about the, so you can also find that if x is a mapping from R is a mapping from x to y and you get x mapped to y, then y mapped to x should also be the answer in that particular subset. Okay. So for example, if you have an element, a set A 1 2 3, and if I draw a relation saying 1 comma 2 2 comma 1 1 comma 3 3 comma 1, so you can see that 1 comma 2, then it has the reverse order also there. For 1 comma 3, it also has its reverse order that is there. So this function is basically, you will say that this function is, this relation is symmetric over here. Okay, so but if I write something of, let's say 1 comma 2 2 comma 1 1 comma 3 and 2 comma 3, then this is not symmetric, as you people can easily understand. So the reason that this is not symmetric is that this is valid, but if since there is 1 comma 3, so there should have been 3 comma 1. If there was 2 comma 3, then there should also have been 3 comma 2, which is not there in this particular relation. So this is not a symmetric. Again, taking an example, so you want, let's say, R3. Now R3 I take as 1 comma 1, 2 comma 2, and 3 comma 3. Now you remember this is also the identity relation. Now can you tell me whether this is symmetric or not? Identity relation. Yes, this is completely symmetric, no problems at all. So because if you say 1 comma 1, right, its reverse would also be 1 comma 1. So you do not write it repeating. You will not repeat it, right? You will not say that repetition will be there. So if you write something like, let's say, 1 comma 1, 2 comma 2, and 3 comma 3, and then you again start writing 1 comma 1, so you know that this is absurd. Though this is not mathematically incorrect, but we don't write because this is already covered here. This one is already covered here. This one is already covered here. So they are already covered. So in a way, identity matrix or sorry, identity relation is already a symmetric relation. I hope the concept of symmetric relation is clear to you people now. Okay, now let's take another case where we need to find number of symmetric relations of a element or of a set A, let's say. And again, A has, let's say, I'll say n elements, as A has n elements in the set. And you want to find number of symmetric elements. Do you remember that we did something of matrix problem in case when we were finding number of here reflexive relations? So we'll follow the matrix method again, right? So let's say A is a set consisting of the first n natural numbers, right? So something like this. So again, what I'll draw the matrix. And now again split this in, let's say, two components, that is diagonal elements, right? Diagonal elements. Why I'm saying diagonal elements? Because I know that these diagonal elements, that is 1 1 2 2 3 3 and all those that are going to come, these diagonal elements, they are symmetric, right? 1 comma 1 is already there, 2 comma 2, they are symmetric. Plus there is non-diagonal elements, non-diagonal elements. Okay, and if I talk about how many non-diagonal elements are there, this is a n cross n matrix, right? N cross n matrix. So diagonal elements are n number, and this will be what? N square minus n, right? So that is why you will get total n square numbers. So now tell me, how many options do you see to be formed for these symmetric relations? Let's first of all talk about the diagonal elements. So let's say 1 comma 1. It again has two options, whether it could be selected in the relation or it could be not selected. 2 comma 2, selected, not selected, selected, not selected, selected, not selected. So for these diagonal elements, the total number of cases can be 2 raised to power n as per the permutation, because each of them could be selected or not selected, and all of them could not be selected. That's also one of the possible cases, right? Then if we talk about these remaining cases, let's say, that is the non-diagonal elements. Let me pick 1 comma 2, and this is the special case. If I pick 1 comma 2, obviously it has two options, selected, not selected. So when I say I talk about 1 comma 2, even if it is selected or not selected, do you understand that 1 comma 2 is completely tied up with 2 comma 1? You cannot talk about 2 comma 1 individually without talking about 1 comma 2 if you are talking about symmetric relation, because for a symmetric relation to occur, if you have 1 comma 2 in your set, then 2 comma 1 should also be there in the set. So if you have selected, let's say, so what will the table look like? If you have selected 1 comma 2, this is already selected, right? Because this has to be in the set to make it symmetric. If it is not selected, then it is already, yes, it is already not selected. So in a way, if you choose this, there is no need to talk about 2 comma 1. Similarly, if I talk about 1 comma 3, there is no need to talk about 3 comma 1. Whatever option that you will choose for this element will already come out for this particular element. So how many numbers are there, or how many pairs are there for which we will talk about selection and non-selection? Yes, that will be actually half of this number. Why half? Because if you see, this is the upper triangle. If you people are very much comfortable with the matrices, so this is the upper triangle, right, from this direction. So if I talk about the upper triangle, so only we have to talk about the elements which fall in this upper triangle, right? because the lower triangle elements are already tied up with their counterparts of the upper triangle region. So that is n square minus n by 2, half of the number, because half will be above the diagonal, half will be below the diagonal. So if we talk about in how many ways you can arrange select them, yes, the selection would be 2 raised to power n square minus n by 2, right? So this is for non-diagonal elements, this is for diagonal elements. What your answer would become then? Answer would be equal to 2 raised to power n multiplied by 2 raised to power n square minus n by 2. This is the answer we were looking for. And if you complete this, this will be nothing but 2 raised to power n square plus n by 2. This is the answer that you will get. So this is the number of symmetric relations that you people can take from a element from a set consisting of n particular elements. And what if we were asked to find number of both symmetric and reflexive relations from a set A? Let's say again the A is n elements in the set, and you were asked to find the total number of relations which are both symmetric and reflexive at the same time. Let's again go to the matrix method that we just did in the earlier two cases. So again, let's go back to the matrix method and understand how we are going to apply this here. So this was the matrix that we had earlier used, right? So let's again divide them into the two components that we did earlier, that is the diagonal elements, right, and non-diagonal elements. Okay, now we want the function to be both reflexive as well as symmetric. So let's first of all talk about reflexive elements. What all reflexive elements will be there? If I talk about reflexive, so that means a comma a should be there. So for reflexive it will be 1 comma 1 should be there, it should be 2 comma 2 and so on. So if you see, these are all diagonal elements. So you want them badly, right? So that means they are already selected. There is no option whether you should select it or not. They are already selected. You can't have any other option. So that means these all diagonal elements this time round are already to be selected. They are done. So now you have remaining how many elements? Yes. So non-diagonal elements, as usually they are n square minus n. Now out of these you can also form symmetric elements, right? And we just did in the symmetric case that if 1 comma 2 is there, so then 2 comma 1 should also be there. If 1 comma 3 is there, then 3 comma 1 is there. So that means the elements in the upper triangle will have their images in the lower triangle, right? And if we select any element in the upper triangle, its counterpart is already selected, right? So that means the number of elements that we want is not n square minus n, but we want n square minus n by 2, because we just need to select or unselect this, select, not select this, select, not select this, these two options, right? The other one has to be the same. If it is selected, so this will also be selected. If this is not selected, then this will also be not selected. So the only option now, the answer to this particular problem is then nothing but 2 raised to power n square minus n by 2. That's it. This is the answer. So these many relations are there which are both symmetric as well as reflexive. We are not multiplying with the diagonal elements this time round. Why? Because diagonal elements have to be selected. You can't have any other option, right? They have to be there. So there is no permutation about them. So that is why I'm not multiplying any cases for these. I hope this is clear. Let's talk about the third property of relation, that is the third type of relation, that is transitive relation. So what do you mean by transitive relation? It says that if there is a comma b, right, and then you have b comma c also in the relation, then definitely a comma c should also be there. A comma b, b comma c is there, then a comma c should also be there in the set or the relation. Then this relation will be known as transitive relation. This is the meaning of the transitive word. Okay, so this is something which we use generally in the quiz problems, that sister of sister and sister of sister type of relations, and this is where transitive relations are being generally used. So if you want to write it in the relation form, it is x relation y is there, y relation z is there, then this applies. If it is transitive, x relation z will also be there. This is the meaning of transitive relation. So before moving on to the question part, these three important points you people have to summarize, that every null relation is symmetric and transitive, right? Just remember the other way, that null relation is not what? Reflexive in nature, but it is symmetric and transitive. Every singleton element or every singleton relation, right? Let's say just A comma B, right, is transitive in relation. So if you are given a relation, because why I'm saying this, because for transitive what you require, that A comma B is there, and if B comma C is there, then C comma A comma C should be there, right? This is what you wanted. But if it is there that only A comma B is there, I would say it is still transitive, right? If there is no B comma C pair, then still A comma B is only set, it is transitive. And why it is? It is a singleton, because it has only this set has only one element. Universal and identity relations are reflexive, symmetric, as well as transitive. Very important. So universal means all the possible combinations of the set. So if you talk about all the possible combinations in a set, they will obviously contain all reflexive, symmetric, and transitive elements. Identity matrices, or let's say, and you remember it as identity relations, you can now understand with the help of diagonal elements. You will not forget. So diagonal elements are all reflexive, symmetric, as well as transitive in nature. All right. So these three properties you people should be very clear before moving further. Okay, so let's start with the equivalence relation. So when do we call a relation an equivalence? So this is very simple. It has to be all the three. That it has to be symmetric, it has to be reflexive, and it has to be transitive. So all these three, if they are there, so then your relation will be known as equivalence relation, right? We will get questions on based on where we need to prove that whether it is a equivalence relation or not, and we'll do them. Don't worry about it. It's just that you should understand what is a equivalence relation. So all the relations which satisfy all the three types of relations is called a equivalence relation. This is what is meant by this. Okay, now let's start doing questions based on what all we have learned till yet, and the questions will be ranging from all the easy questions to the mediocre questions, so that you do not need to do questions apart from the questions which are covered in the video itself. So let's start the first question. It says if a set A has three elements A, B, C, then find the number of subsets of A. Obviously you have done this, so number of subsets or the number in the power set would be 2 raised to power n, that is the formula. And if you see that the number of elements here is 3, so n is equal to 3, so the number of subsets is nothing but 2 raised to power 3, as simple as that. So it is nothing but 8. And they also want that you should mention the sets that will be formed. So the subsets of the subsets formed by using the elements of the set A would be, I can say it will be, first will be the phi null element, then you can select A, then you can select B. We just did this earlier, remember? And then you can select two at a time, that is A and B. Then you can select B and C, then you can select C and A, and then you can select all the three in a particular subset, right? And if they were, in fact, we also did, they could have asked you number of proper sets. So then what will be the number of proper sets? Yes, 8 minus 2, that is 6 will be the number of proper sets. In proper sets, what we do, we delete the null set and the set itself. So you see, this is the set itself and this is the null set. So number of proper set will be 6. Let's move to the next problem. So this is something, a very famous problem which is generally asked at your board examination. It says find the number of elements in the power set of empty or null set. So when I say power set of this, what do you understand by this? So how we will write this is, power set of this is nothing but first of all the phi element and the set phi both. So there is a difference. This is the element phi and this is the set phi. And if I again take the power element of this particular now, so let me tell you how the things are formed. First would be the null set, then would be the set of null set, null element, then would be the set of null element, and the fourth would be that these two are there selected, like this. So this is what is called power set of null set. So you can see easily there are how many elements? There are 4 elements in this, and that is why you are getting answer as yep. And even if you want, you could have actually used the formula that we just did, the number of elements 2 raised to power 2 raised to power n. You just need to replace n here as 1. So your answer will be 2 raised to power 2, which is again 4. This is what we did for number of power elements, right? You remember? Yes, so for power elements, you can do something like this. Let's move to the next problem. It says A and B are two sets, each contain 3. So NA is the cardinality is 3. The cardinality of B set is 6. What can be the minimum number of elements in A union B, and what could be the maximum number of elements in A union B? So this is something related to the set problems, right? A union B. So number of elements in A union B. How can you rewrite them in terms of A and B? So n of A plus n of B minus n A intersection B, right? So this is now given to you that NA is 3, this is 6, and this is what you need to. So depending on the value of this particular answer, you will get the value for A union B. So you want, let's say, first of all, the minimum value of A union B. So if you want minimum value, so that means the maximum number should be subtracted. So for this, what you will want number of elements in A and B which are common to be maximum, right? And what could be the maximum figure? Yes, it will not be 6. Remember, this will not be 6. In fact, it will be equal to 3 because n has only 3 elements. All of them are common with, yes, see, so you can say this happens when A becomes subset of B, then you will have what? Minimum value of A union B. So this becomes nothing but 6. Now you also need to find the maximum value of A union B. So here I'll again rewrite the expression. This is in A intersection B. So the maximum value will be obtained when actually nothing is subtracted, right? If you do not subtract any number, then this will be the maximum. So this will happen when A intersection B is 0, and this happens when they are, yes, correct, they are disjoint sets. That is, there is nothing common between them. So the maximum value is 9 and the minimum value is 6. This is what you will say for this answer. Okay, let's take the other problem. It says if the number of elements in A is n and the number of elements in B is n, then the number of elements in the power set of A cross B will be what? We have already done this. This is very simple. So A cross B. So how many total sets could be there? This has n elements. This has m and n elements. So answer is nothing but m cross n. We just did the proof, remember, in the Cartesian product. So there is something related to Cartesian product. So for total number of elements in the Cartesian product will be m cross n. In fact, the answers to both the problems. So here it is said number of relations. If you talk about number of relations or you talk about power set, it is one and the same thing, right? So power set and number of relations, total number of relations is one and the same thing. The answer is m cross n. Very, very simple problem. Okay, so here there are again questions which are saying that x is a set and y is a set. X has 3 elements, okay, and this particularly is a function relation where you are trying to find number of reflexive relations. Okay, very interesting. Let's see. x1, x2, x3 are the elements in the set X. Y set has 5 elements: x1, x2, x3, x4, and x5. Right? These are the 5 elements. Now let's say there is a relation R1. So for reflexive elements, so reflexive relation, what would be a reflexive relation? So first of all, it has not been given. So the relation is being drawn from x to y. All right, let's assume this, that the relation is from x to y. Then only the question will make sense. So if this has to be reflexive, what are the minimum elements which should be there in the set? So it should be, if it is reflexive, so x1 should be there, then x2 should be there, and x3 should be there. Then only the function will be, if this relation has minimum, so it should have minimum these 3, right? If there are minimum these 3 available, then only we'll talk about the property of reflexive. Now let's go on and see. R1 has x1 both, x2 both, but not, yes, so this is not a reflexive function. Yes, this is completely a reflexive function, right? Next, talk about next. x1, y1 is there, x2, y2 is there, x3, y3 is there, and apart from that x1, x3 and x2, x4 are there, not a problem. We have actually satisfied that minimum these three should be there. Apart from that, anything extra would be a reflexive function. Now again talking about this here, it is x1, x2, x3. So it is reflexive? Yes. So this is the basically the common error that everybody does here. This is not reflexive. Now can you tell me why it is not reflexive? Yes, some of you have been able to identify. Why? Because here x4 comma x4 is there. Do you have x4 in the set X? So where does this element is coming from? So x4 actually does not belong to your element X. So this should not have been here. So again, this is not a reflexive relation. Got it? Okay, let's take another. It's now again the same kind of stuff, and now it is asking you to prove which one of them is a symmetric relation. So again, X has 3 elements here, and Y has your 6 elements: A, B, C, D, E, F. Right? Now let's start doing this. So R1 for symmetric. So for symmetric, what do you understand by symmetric? So if symmetric is A comma B, then you should have B comma A. Right? If there is A comma C, then you should have C comma A. This is the meaning of symmetric. So R1 is a void relation, right? So we know that R1 is a void, and we just talked about that if it is a null set is always symmetric and transitive. So that means this is a symmetric function, that is not a symmetric relation, not a problem. R2 given here is simply A comma B. Now obviously this is not symmetric, NS not symmetric. Why? Because if A comma B was there, we wanted B comma A to be here. Let's talk about R3. So R3 has A comma B, then it has B comma A. So these two are correlated. Then you have A comma C, and then you have C comma A. These two are correlated, and then you have A comma A. A comma A is already related to itself, right? We do not want to write A comma A again. So this is no problem. This is symmetric, right? No problems at all. So this is also symmetric. So this is symmetric. This is symmetric. The R2 function is not symmetric. Just remember that a void relation is always symmetric. It is symmetric as well as transitive. Let's take the other problem. Now this is finding the transitive theorem. Okay. So I'll write X first of all for you people. X is given to be A, B and C. Y is given to be A, B, C, D, and so it consists of 5 elements and X consists of 3 elements. So R1 relation, it's a null set. Yes, null set we already did. Null set is, yes, it is transitive in nature, no problem. Null set are always symmetric and transitive, so A is correct. Let's talk about the R2 one. R2 says it has A comma A. So isn't it a singleton? Right? Singleton, because it has only one element, singleton. And we just did a property that singleton are always transitive, right? So again, R2 is no problems. Let's talk about R3 then. R3 has A comma A, right? And then it has C comma D. So again, it is a set of 2 singletons. In fact, I should not say it's singleton, but yes, A comma A has again no bearing with A. This has no correlation. So for something of transitive, you need XRY, YRZ to say XRZ, which is not happening here. So I would again say that this is transitive, not a problem with me at all. So C is also transitive. Let's talk about the function 4 or the relation 4, sorry. So it is A comma B is there. And then you have B comma C. Now you can strictly talk about the transitive A comma B, B comma C. So A comma should be there. Yes, which is there, you can see. Then you have A comma A, no problem with A comma A. And then you have C comma A. That is also not a problem if we have a C comma A. So let's see, A goes to C, C goes to A, then you also have A comma A. Perfect thing. So in fact, I could say this is completely transitive. Why? Because you have 2 pairs of transitive theorems which are actually satisfying. This is the first triplet, and then this and this is the second triplet. So all the 4 in this particular example are transitive. Okay. Now let's say a question on where we want to prove whether the relation is equivalence relation or not. It is given that prove that the relation R on the set of Z. Set of Z. Z is nothing but set of integers, right? Z means set of integers. For all integers defined by X comma Y. So how the relation is now being defined over X and Y is that R is a relation where x minus y is divisible by n, right? Or in fact, if I condition this in terms of maths, I can say x minus y is equal to np, where p is also a integer, right? This is what you can tell very easily by mathematical definition. Now we want to find that whether it's equivalence relation or not. So for equivalence relation, what we people do? Yes, we'll check for all the three properties, right? So let's start with the reflexive first of all, which let's take this in the order. So reflexive. So what do reflexive says? So if A belongs to a element A, then A comma A should belong to your relation, right? So let's try this. So you want to say that x comma x will lie in this relation that is given to you. So what the x minus relation will become? X minus x. So x minus x is nothing but 0, and 0, so you want to say 0 is divisible by n, which is completely true. So that means this function is reflexive, no problem at all. Let's talk about the symmetric part now. So for symmetric, what you say that if A and B both belong to A, then if A comma B is there, then B comma A should also be there and belongs to R. Alright, let's try this out. So you say X and Y both belong to R, and we say that this releases that X minus Y is divisible by N. So now you want to prove that the opposite of it, that is Y minus X, is divisible by N or not. This is what you are asking. Obviously, if X minus Y is divisible by N, Y minus X is also divisible by N, no problem. So it is also symmetric. Let's talk about the transitive part now. Right, the first two parts are, I hope, completely clear to you people. So transitive says that let's say A, B, C belong to the set. If A comma B is there to the relation and B comma C also belongs to the relation, then A comma C should belong to the relation. So how I am going to apply this in this particular problem? Let's see. I take X, Y and Z as the elements, right? For transitive you require three elements. You say X and Y belong to the set relation, so you will say X minus Y is nothing but divisible by P, so I can say n times P1, right? You say Y comma Z belongs to R, so this means Y minus Z should be divisible by N, and let me call this as P2, and I know that P1, P2 themselves belong to set of integers, right? And then the third thing that you want to prove, now what you want to prove here is that whether X comma Z is there in the relation or not. So if we talk about X comma Z, what we can say? So X comma Z belong to relation would be X minus Z. So for X minus Z, what you people can do, you can add the first two. If you add the first two, what you will get? NP1 plus NP2, or take n common, P1 plus P2, right? Now can you say that X minus Z is divisible by N? Yes, we can say so. Why? Because here P1 and P2 are both integers. So P1 plus P2 will also be integer, right? So that means this is X minus Z is also divisible by N. So that means it is symmetric or transitive also. So it has all the three properties. That is why I would say this relation is a equivalent or equivalence relation. This is how you need to solve questions based on equivalence relation. Okay, let's take another problem where we want to prove whether the function is equivalent or not, or in fact I have rewritten it, show that R1 is reflexive, symmetric but not transitive. So what is R1? First of all, you say that A comma B belong to R1, where R1 is defined as 1 plus AB is greater than 0, right? 1 plus AB is greater than 0 for both A and B lying on the set of R's, right? Set of real numbers. Okay, let's try the first property, that is reflexivity, right? Reflexive in nature. For reflexive, you want A comma A to be in R, right? And we know that A belongs to set of real numbers. Let's apply this now. So it will become A into A, right? So this will be 1 plus A square. And we know that A square is always positive. 1, if you add, this is greater than 0. And we wanted that the relation should be that LHS, that is 1 plus AB, should be positive. which is happening. So this is reflexive, no problems at all. Okay, this is reflexive. Let's talk about symmetric. For symmetric, what you want? For symmetric, you will say a comma b belongs to R, then b comma a also belongs to the relation, right? Let's see. So you have 1 comma ab. So this is assumed, this is given, right? Don't worry about this because I say that a comma b is in a relation. So 1 plus ab is there. So what will be b comma a? So b comma a will be 1 plus ba. What can you say about 1 plus ba now? Will it be positive? Obviously, if 1 plus ab is positive, 1 plus ba will also be positive. Hence, this shows that this is symmetric as well. So symmetric and reflexive are done. Let's talk about the transitive part now, which is, we are already given that it is not transitive, right? So transitive, we know that if we need to find such answers where a comma b belongs to the relation, b comma c belongs to the relation, but a comma c does not belong to the relation, then it will not be transitive. Okay, so if you want to solve for transitive, can you give me a small answer now? A very simple answer. Let's say, I'll take an example here. If you find even one example which will make it non-transitive, then it will be non-transitive. Let's say for a comma b, I take this as 1 comma 1 by 2. So what will be 1 plus ab here? Yes, it is greater than 0. So it is satisfying the relation. So that means a comma b belongs to relation, right? Now for b comma c, let's say I define this as 1 comma 2, right? Comma minus 1. Now what will be the value of 1 plus ab? It will still be positive. You can see it will be half. Here it will be 3 by 2. Here it will be half. So that means b comma c also belongs to R, right? Then you need to find transitivity, right? For transitivity, you will check a comma c. So what will be a comma c now? A comma c will become 1 comma minus 1 because just see that a is 1 and c is minus 1. So this will be 1 comma minus 1. So what will be the value if you just put it here? Now this will not be greater than 0. It will become equal to 0. So that means a comma c does not belong to the relation, right? Does not belong to the relation. So in fact, you have got one particular case where it is not transitive. That is why I would say this is not transitive. And in fact, in boards also, you can find and prove like this, where you take a one particular case which does not satisfy the transitivity, then you can say the function is not transitive at all. I hope the question is clear. Okay, let's take the other problem, which is basically on the inverse relation. Let's see what it says. It says A is a set of first 10 natural numbers. So A is nothing but set of first 10 natural numbers. So it is something like this, right? 9 and 10. Okay. And R is a relation defined on A. So X comma Y, right, is a relation where the relation is defined by X plus 2Y is equal to 10. And what will be 2y then? 2. You can just now simplify the function and the relation will be something of this particular sort. So this is the relation in terms of x and y. Also note x and y are taken from which set? Now see the definition of relation. It says R is a relation from x to y where x is also from A and y is also from the element A and x plus 2y, and this is how they are mapped. Now you want to find R and R inverse. So first of all, let's talk about just R. Okay. So the first is you find domain of R. Can you tell me what will be the domain of R? Yes, the students do a mistake here. So they say the domain of R, so X belongs to, yes, first 10 natural numbers. This is what they say very quickly, because they say that X is belonging to A is a set of, right? No, this answer is completely wrong actually. So what we need to find, you want to find those x and y values which actually satisfy the relation. So now let's talk about this. So your y here is y is equal to 10 minus x by 2. Let's start by putting x equal to 1. What you will get for y? You will get 9 by 2. Does this value belong to A? No. So that means this will also not belong to A. So x equal to 1 does not belong to the relation. This is how you should see it, because you are not getting a value of y which should belong to set A here. So if I put x equal to 2, you will get y equal to 4 now this time around, which belongs to A. So that means this is also belonging to R relation, right? So the values, if you start solving, you can easily see that only the even values of x will help your case. If I talk about x equal to 10, can you tell me what will happen with 10? So in case of 10, the value of y will come out to be 0, which is again not a part of A. Hence, this value of x and y will not belong to R. So the only possible values that you will take is 2, 4, 6 and 8. So this is what you will call the domain. So domain of R is nothing but x can take values 2, 4, 6 and 8. We know that the range is nothing but the values which the y can take corresponding to the values of x. So now just calculate the values of y at this. So what will be the value of y here then? Can you tell me what will be the value? So here y is 3, here y will be 2 and here y will be equal to 1. So the range of R will be nothing but these 4 values. That's it. So if I have to talk about the range will be 1, 2, 3, 4 for R. So this is your range of R. This is how you solve this. And if we want to ask for your inverse relation, so inverse relation. So now understand this fact. For inverse relation here, it is a very simple definition. So domain of R will be equal to range of R inverse. That is range of inverse function. And the range of R will be equal to what? Yes, it will be equal to domain of R inverse. As simple as that. Just remember these two laws. Okay, so these two laws are to be remembered. So if you just check this out, so we just did domain. So this is the domain. So this becomes actually the range of R inverse. And this range of R will be nothing but domain of R inverse. As simple as that. Okay, so for relations, this property is valid. Do not confuse it with inverse of a function, where we used to check, we used to say that range of R is equal to domain, but the domain of R is not equal to the output of the inverse. Just keep it simple that in case of relations, they are vice versa, each other. So you have already found the domain of R. So this is range, right? And range of R will be domain of R inverse. That's it. This is how you solve. I hope the question is clear now. Alright, so by this we come to the end of this particular chapter, that is set in relations. I hope the chapter was clear to you. I have made sure that I have covered all the type of questions which are actually asked of the relations topic and which would fetch you the 4 marks in your JEE Mains exam. In fact, the video will help you tremendously at your board level preparations also. So watch the video again and again to understand the concept that are involved in this particular topic. You need not do much more than the video. It's self-sufficient, no requirement to do any extra stuff. I will be sending you the worksheets. Do that. Do the NCERT that is there with you or the board textbook that you people have. More than sufficient to fetch 4 marks at the entrance examination level. Okay, so I'll see you with the next chapter day after. Good night.